ongoing developments of HMSC and planned developments of HMSC. So there are a lot of things in our mind, and many of them are based on like feedback from users that what would be nice to develop in this context to make the package more useful for researchers, and here we want to discuss some of those things under these 4 themes here. One is that it would be nice if it fits the models faster than it does now, that sometimes it's no issue that you can fit your model in minutes even, or it doesn't take any time, but then for some big data, we have users who say that, oh, I have fitted the model for 3 months and it's still not finished. That would be great to scale it up. So that's one thing. And then another thing is that would be nice to have also other kinds of data models than those Probit and normal and log normal Poisson that we have now. Then we have implemented this as this kind of a hierarchical model with the, the motivation is the kind of the community ecology theory in the background, that we try to capture some processes that we know drive community assembly over space-time and environmental gradients. But of course, there are some kind of processes that we don't even try to address, or that would be nice to try to capture in this modeling framework as well. So that's kind of the new model structures related to ecological and evolutionary processes. And then the 4th bullet point is stability and usability of this R package HMSC, like the features of the R package itself. And I will talk about the 3 first of these shortly, utilizing some material that I got from Gleb. And then Jari will talk about this last part, last bullet point. And first about this computational efficiency, would be nice if the models run faster. I think, Lev, your slides that you presented somewhere else, they had more detailed material on that, but I skipped the technical details, some of the technical details, as I think for the users it's just nice if it fits faster, you don't need to know so precisely why. So something that is here under published and implemented is better MCMC mixing via collapse Gibbs updaters. So that's something that I guess especially Gleb has been working with, that now some models converge faster. You need less iterations because the sampling is done in a better way. But then what is in progress? The biggest thing is this efficient HPC and GPU compatible implementation. So HPC means high performance computing, and GPU are these graphic, what is GPU? Yeah, graphical processor instead of the usual CPUs that you have in basically all computers, that if you have GPUs, they can do some operations much faster and they could be utilized. So that there is this plan that if HMSC or the computational part of HMSC is like recoded using, for example, this TensorFlow and GPU computations, it can be made faster. And there are some proofs of concept that some of the most computationally intensive part can be done, for example, 300 times faster, especially for big data. That for small data, it necessarily there is no speed up, or maybe it's even slower. It doesn't matter because small data you can fit fast in any case, but for big data, it can make a huge difference, and then it would be great just to implement this kind of a thing, so that then you could fit the model that now takes a year, you could fit that in a day. So that would be nice. And this is an ongoing project that we have a team starting to work on this, or already Gleb has done quite a lot of kind of preliminary work on this, but we have also like a new person recruited to specifically focus on this part, so we hope that this will happen at some point. Okay, and then there are some other, let's say, more minor developments that I mean important, but they don't concern like the whole package as such. That now, if you include a phylogen in the model, it's no problem if you have 100 species or something like that. The computations are equally as fast. But if you have 1,000 species or 2,000 species and you include phylogeny, that really screws up things, because the way that we have now implemented the estimation of the phylogeny, I guess they more or less rely on this basically inverting or calculating the velocity of this correlation matrix, the species-to-species matrix, and then things scale very badly when you increase the number of species. So GLEB has been implemented another component, other way to estimate the phylogenetic signal, which then scales much nicer with the number of species, which would mean that even if you have many species, you can still include the phylogeny without screwing up with the computational times. Okay, numerically scalable spatiotemporal latent factors. This is not about just scaling up computational efficiency, but bringing in a new model component, which is a spatiotemporal random effect. As now we have just, you can put main effect of space and time, but not the kind of the product between those two. So this is another development to bring like Kronecker products of different kinds of random effects as one case, spatiotemporal random effect. And why I now put it a little bit arbitrarily to this slide is that typically that will be difficult to fit computationally. I mean, it's very easy to write down the model. You just write the model and add the equations that one Kronecker product, and that's the model we want to implement. But then how to do it? Maybe not conceptually so difficult to do, but how to do it in practice. If we have spatiotemporal data, and if the data are such that there is some hope in estimating spatial signal, temporal signal, and spatiotemporal signal, then you have a lot of data points. Otherwise, it doesn't make. Otherwise, there's no need for spatiotemporal model. And now, if you have these 10,000, tens of thousands, or 10,000, or whatever number of sampling units, you want to fit the spatiotemporal model, estimate those alphas for space-time. It's computationally difficult, and that's something that is in progress. Do you want to add anything to this part? Yeah. Yes. Okay. Did you have your microphone on? Do you have your microphone on?
Well, I would just like to repeat that, like, this phylogenetic component, which would be scalable to, well, effectively tens of thousands of species probably, it's not yet in implementation, so it's still a bit of in development on the statistical level, not on the package level.
In the chat there was a question about, can we get the script from this morning? I will email that to everybody when this session is over and we go to the breakout sessions. Okay, if it's not in the web, I will email that as well and put it to the web. Okay, that's about the computations. That we want to make HMSC do the same things as now, but faster. And this doesn't, I mean, this that things get faster, like computers have been getting faster and faster, like over the past tens of years. It doesn't mean that you wait less time. We still wait as much as the researchers waited like 10 years ago, because, you know, you can wait a week or a month, but you don't want to wait, you know, 5 years. It's just that you can then fit bigger models. That's what happens in practice. Okay, then this more flexibility with data models. Now we have this linear model, profit model, log normal Poisson model, which look like that. So would be nice to have more and maybe also in some sense better working models for zero inflated data, such as the negative binomial or something like that. I don't remember if we have anything here even like in plans, but just saying that would be nice to have those. Negative binomial is in plans. Great. Yeah. Multinomial data. That would be actually very nice. That we could model, for example, I mean, this kind of a data that you have like 10 categories. That, I mean, an extension of the 0-1 model, of the profit model, that you don't have just 2 categories, 0 and 1, but you have like, let's say 10 categories, that is either this species, this species, this species, or this species, like from the sequence data. And then like, you basically model this vector of what's the probability that your sample represents each of those species. So multinomial data model would be much more natural for especially sequencing data, but also some other data, than the way that we treat it now. That, you know, now we were modeling this sequence abundance using, for example, this log normal model, this abundance conditional presence. What is the weakness of that is that we look at each species separately. I mean, not fully independently, but more or less independently in this sense. If I make a prediction by that model, I sum the predicted sequence count. They don't sum to the total sequence count that we actually had. Whereas in reality that constrains it, and the multinomial model would be more natural. But that's not implemented. I guess you can approximate that by using this Poisson model and doing some tricks, but still this multinomial is not implemented yet. I don't think this is like a major limitation. I mean, I'm still quite happy to analyze sequence data myself with HMSC. Some reviewers get like really crazy about this, that you are having the wrong data model, because in the statistical literature of how do you do like a statistical analysis of microorganisms, there is very much emphasis on this, that, you know, you have, this is the data model that you need to use, and if you don't use that, then you can introduce these spurious correlations, that you see a negative correlation just because of this artifact. That, let's say that is the case that you have only 2 species that come out from your sequencing data, and you have 10,000 sequences in total for every sample. If in this first sample, and there is nothing else than these 2 species, if in the first sample you have 1,000 sequences for species 1, we know already that the second one will be 9,000 sequences, because they sum always to this total 10,000. And now this would introduce a negative correlation between these 2, which maybe has no biological origin. So in theory, you can generate these kind of negative associations because you have the wrong data model. In practice, I don't think this is really the case in our applications, where we typically have like many species, and it's not so that these 2 dominate, but, you know, there's like a spread of many species, and then there are a lot of sequences going to this unknown category as well. But it's something good to keep in mind. But then if you look at this literature on the microorganisms, they really care about this. There are papers with the title that you have to use this approach. It's mandatory. But then they very often in applications, they completely, for example, ignore the study design, because many of those software, they don't, for example, implement random effects. You cannot account for the study design or things like that. It's, in my mind, are much more important than this. And in many, I mean, depends on the case, but in many cases they are. So it would be nice to be able to do like all of those things that are natural to do and that people care about, and that's why the multinomial data model would be nice here. Then the other data model that would be nice to have is point pattern data. That now we are working with the sampling units. That there is always some sampling unit where, for example, the species is present or not. But then a lot of the data in ecology are about point patterns. That what we have, for example, in GPIF or this kind of data are that exactly in this coordinate a species was recorded. There's like no sampling unit where it would be present or absent, but it's like in continuous space we are given coordinates where species have been found. This is point pattern data, and of course it can be also spatial. There can be a temporal aspect. There can be spatiotemporal data of this sort. And then this kind of a data you typically analyze with something like maxent or then like this log Gaussian Cox processes that what you are predicting with these models is not the presence absence but the intensity. Like in this part of space, what is the density of space per unit area, what is the expected number of points that there are there, given the covariance and the spatial location. So that kind of a data model could be implemented in HMSC, and actually we have started that many years ago, but then it was like a bit left behind the background because of some technical issues and lack of doers, but it's something that I guess we hope to implement at some point, and then you could use HMSC to analyze like multivariate point pattern data in this way. Now there's one thing that I want to say about this point pattern data is that a lot of the point pattern data that we have are these presence only data, that there's like no controlled sampling effort. So that you see that, okay, these are the locations where somebody found the species. We don't know if it's present elsewhere or not, which makes the analysis of this data very difficult because, you know, maybe we see the species where it's found just because it's actually present everywhere, but this is where people look for it, or maybe it's actually present in those places only and it's not present anywhere else. We don't know if we just see the data, the data doesn't tell. So a lot of these point pattern data have this presence only aspect, which make them more tricky to deal with whatever method you are using, because you have to assume something about the sampling effort implicitly or explicitly. But then we can have point pattern data which don't have this issue that, you know, maybe somebody went to the tropics and surveyed their 1 hectare plots and actually recorded the location of every single tree species individual that was greater than some size in the diameter. There are these kind of data sets available. That's point pattern data. That is kind of perfect point pattern data, that there is more or less no detection error. So whether your data is the point pattern data of the first or the second type, you know, you could analyze it with these kind of models. Okay, then data matrices with uncertainty. There is uncertainty and then there's missing data. Missing data is not mentioned here, but let me first reiterate that you can have missing data in the Y matrix, like we did when we had the hurdle models. We cannot have that in X, T, or C. I don't know if we want to ever have it there. But then uncertainty, especially for the data matrix Y. Now when we say that the species is present or absent, we say that we know if it's present or absent, but there is not uncertainty. And I don't need the kind of uncertainty that maybe the species was there, but we didn't observe it. That's the next bullet point. But we can have other types of uncertainty. For example, maybe this data comes from DNA sequencing, and then there is uncertainty related to the taxonomic classification. Our taxonomic classifier says that this species is Formitopsis pinicola with 90% probability, but with 10% probability it can be Formitopsis rosea. You cannot fully confidently say from the sequencing data there remains some uncertainty. So this kind of uncertainty we could in theory bring into HMSC so that it would know that this response matrix, you know, is uncertain about this or some other aspect of the data. That's in theory quite easy to do in the Bayesian model, that instead of bringing this fixed matrix Y, we bring kind of a distribution of those matrices, some kind of a prior distribution of the matrix, and then part of the estimation is to estimate then the true matrix. And then there is this explicit separation of the process model and the observation model to bring these detection models, like occupancy models that a lot of people have been asking for. We haven't implemented that partially because I think you can account for that by having these random effect structures, and partially because you actually need quite specific data to do these occupancy models. You have to have those repeated surveys in over short time intervals so that the biological state remains the same, and then it's just the detection that varies. Of course, there are such data sets, but like I haven't collaborated with any data set where we would definitely need the occupancy model that would be the most natural. So we haven't had like a strong push to implement that from our own needs, but of course it would be nice to do. But then also all kinds of other observation models would be nice to have. Any questions about or comments about this part, about the data models? Okay. If not, then the last slide from my side before going to Jari's part. It is about model structures related to ecological and evolutionary processes. So here you see the kind of the DAG of the current HMSC, or the simplified DAG of the current HMSC. It shows like what are the links between the parameters and the data and the structure of the model. And then some things are highlighted here that what kind of extensions we could have. So first there is this influence of phylogeny on species niches, and this is something that we discussed already a bit. We could have more flexible and/or mechanistic models to account for species evolution via phylogeny. For example, we could have this kind of a weighting that we could allow the model to ask that did the past, very past deep evolution matter more, or the more recent one. Maybe the most important development here is that our model now assumes that all the responses to all covariants have the same phylogenetic signal. So we actually want to estimate some kind of a vector of rho, like one per covariate. That's one ongoing development. This has been implemented to some development version of HMSC that it's kind of up and running, but it's not in the main package. Then second point. Now we have this link from the species traits and phylogeny to the betas. We can ask that how much of these responses of the species to the environment can be explained or attributed to the traits and the phylogeny. So the link from environmental filtering to traits and phylogeny. But equally well, we could ask that how about the biotic filtering, or the species interactions, or the species associations in practice? Are those somehow structured by traits and phylogeny? Is it so that related species tend to be found together, or that they tend to have negative co-occurrence? And how about with the traits? And this is one development plan which is also like at least partially implemented, that how do we bring the traits and phylogeny to the association matrices. This is actually something that none of the joint species distribution models do at the moment. I think there is no model that would do this. I mean, among these different versions of joint species distribution models, it's a bit tricky to do. And like long time ago, like one initial idea was that let's just model it in the same way as we model these fixed effects. That betas are the responses of the species to the measured covariates. We now have this hierarchical layer for them. Lambdas are the responses of the species to those hidden covariates. Let's model their relationship, like them with the help of traits and phylogeny, exactly as we do with betas. But I think this model could be implemented. Is maybe technically not so difficult to do it, but then clearly one shortcoming of that model is that it can only lead to the situation where related species tend to have a positive association and species with similar traits tend to have a positive association. That model would not allow for a situation where species that have similar traits or close to each other in phylogeny would have a negative association. And I think it's reasonable to have this thing for fixed effects, that if you have species with similar traits, they respond in the same way to environmental variation. But if these species associations really would model the species interactions, you would actually expect to see cases where species with similar traits have a negative association if they compete for the same resources, for example. So this simple way of doing this model wouldn't allow for that. And now that's why the version that is being implemented by Lorenzo, a collaborator that we have from Italy, and the usual suspect, Leb, that actually models the prior structure of these latent factors with the help of the traits and the phylogeny. So then it kind of uses the traits and phylogeny to influence which species are associated to each other, but not whether they are positively or negatively. Okay, what else do we have? Network modeling, including possibility of bringing prior information about known interactions and unfeasible interactions. So quite often we also have direct data on species interactions for the same species for which we have occurrence data. Or maybe not quite often, because we try to look for this kind of data sets and we didn't find many, but sometimes you have, and in the future you could have more. So the data sets that we are looking at in the context of these developments are, for example, this frugivore data from Brazil, where you have data on, you have occurrence data on plants, like trees mainly, and then you have occurrence data on frugivores, like, for example, birds and monkeys and whatever species groups you might have there. And then you have some direct data on interactions. Which bird eats the fruits of which plants? How do we bring these data together? Currently, with HMSC, you cannot do it, and there are not many, maybe other approaches where you could, in a nice way, bring those data together. And now, of course, those direct data on interactions, they are direct data on interactions, and interactions are somehow part of the HMSC, not equally explicitly. How do we combine these data? We are trying to combine them in two ways. The more trivial way from the modeling point of view is that let's just use HMSC to model species distributions. Let's not care about the species interaction data at that stage. But then after we have more predicted the species distribution, so for example over some continuous space over grids, let's then use the species interaction matrices to then predict which species pair would interact in each location. So that's one kind of a way where you don't need any modeling development, you just apply these approaches. But then the more ambitious approach is that can we actually use this direct information about species interactions to make better predictions on species occurrences and co-occurrences? So that's something that is like a more ambitious project to try to address this by either applying the models that exist in some way or then developing these models so that species interactions are somehow directly part of HMSC. Yeah, it's this question 6 partially. Yeah, can network modeling be used to disentangle species associations from real interactions is part of the same question. And then there is this 7 individual level perspective, incorporating collected meta-info on studied individuals. The simplest example of this is that sometimes we have those traits measured at the individual level, not just the species level. But at the same time as your survey communities, you measure traits for each individual or subset of the individuals in that population. What you can already now do with HMSC is to jointly model the species occurrences and their traits by putting the occurrences or abundances as some columns and then the traits as other columns. And obviously those traits you model conditional on presence, because if the species is not present, you cannot measure the traits. And in this way, you can already do some of this modeling. But then, of course, you could think about how to extend HMSC to more explicitly account for this next hierarchical level. That we have the community level that we model, we have the species level that we model, the individual level we don't at this point explicitly model. I think here also a major limitation is the lack of data. But we tried to find nice data sets that would be such that you could model the species occurrences or abundances nicely with HMSC. Nicely means that you have ideally more than one species, and then you have like at least 50 sampling units that you can build a meaningful model. But then additionally, you would have this trait data that would be rich enough that you could also look at that. I don't think there are too many data sets because we have problems identifying those. Here, I haven't looked at DNA sequence data in this context. I mean, if we would do it, then like if you think about those fungal DNA data sets that we have, there we have sequenced only one marker, this ITS2. And that's basically for species identification. You cannot really infer individual traits from that. But if you would sequence some other traits, sequence some other markers that would, bring this kind of a more functional trait information, then that would be one possibility to generate such data sets, but maybe they exist already. Okay, so that's the end of this part. Now, if anyone of you has a fantasy about any other feature that you would like to see in HMSC, the floor is yours.
I'll use the bird transect data as an example because we used this previously, but different bird species, they have very different observation probabilities, kind of. So for example, if there's a cuckoo along the transect, you can be quite confident you're going to observe it. But if there's some bird of prey, they can be really elusive during breeding season. So is there any way to incorporate the observation probability in HMSC?
Yeah, so with the bird example, what we actually modeled, I mean, what was the CR1 that we modeled with the probit model? It was the probability that, if some, like if you think about predictions, for example, when we produced the species distribution map, it didn't show the probability that the species is present in that grid cell. It was the probability that if somebody would go in this to this grid cell, do a 5 kilometer typical transect, what is the probability that that species would have been observed? So that the data and the model, they completely confounded the observation process and the biological process. And now this question that how do we tackle this observation detection process, and also the fact that the detection probability is different for different species. Well, let's first assume that we have no other data available than the data that we have now, that we just have the counts of the birds or the presence absences, and we don't have repeated surveys over the season. And so let's assume that we have exactly the data that we used in this case study. I don't think there is more or less any way to separate those detection and the occurrence probabilities from those data, whatever statistical method you use. Because you can generate the same data with, like theoretically, with perfect detection, or the other extreme that all species are everywhere and detection varies, basically, possibly with covariance. So I think this is, before like we are like, oh, we should use some other approach, we have to think that is there signal in the data about this detection, and I don't think there is in this case. If we look at only the data that we looked at now, but then of course we can have other kinds of data. We can have some prior information about how difficult it is to observe the species. We can generate some calibration data. We can ask several groups to do the same transects, in the same day or consecutive days or whatever, and then that will give us very, very direct information about the detection probability. Or then we can do, of course, this like distance counting, that which is this method that is used in bird transects, that you don't only record that the species was there, but you estimate how far from the transect line the species is. If you do that, then you can fit to this model. To this data, you can fit an observation model which estimates how the detection probability decreases with distance. So let's assume that you have some of these kind of data types that you can separate detection from the actual presence of the species, then that the species do vary in their detectability, which is what you asked about, then that's of course easy to account for, because we estimate these detection probabilities separately for each species, and then we can account for that. If you would have this kind of data, this distance count data or repeated surveys, I mean, as said before, you can analyze it with the HMSC, but you cannot analyze it in the sense that you cannot do it exactly in the same way as occupancy models, that you model the probability that the species is present, and then you multiply that with the detection probability, but you have to do it a bit differently. I don't know if I answered your question.
Yes, you did. Continuing the bird example, there's already this observation constant kind of for each bird species that are used if you are trying to estimate how many pairs are breeding in certain area, then you do the transects and use the robust observation constants. So if you already have the observation probability constant for each bird species, is there any way to right now to incorporate it to HMC if you are trying to model how many actual birds are breeding in that area?
Yeah, so that you say that there is this kind of a calibration data, that somebody has made this kind of a calibration formula that, if you see on average like 3 individuals in a transect, that means that you have 20 breeding pairs per hectare or per square kilometer. That this kind of a conversion formula exists. Yeah, so sure, then you could bring them into HMSC in one way or another. Of course, the easiest way to do that is to incorporate them into the post-processing. But now that HMSC predicts that there will be 3 individuals per transect line in this place, then you just use this formula to say that means this many breeding pairs per hectare. That's maybe the most straightforward way to do it. But then possibly you could also bring it somehow that into the model, but I don't know I don't see straight away why you would do it. Yeah.
You thought of this asymmetric response?
Yeah, the asymmetric association matrices that I want to talk with you, but you don't want to talk with me, kind of things. So when we have this kind of a snapshot data, then as said, it's I don't think there is signal in the data that you could separate it, like why we are together. Is it so that who wants to talk and who not? It's just the case that we are together, like more often or less often than by random. But then from this time series data, you can find it out that in these lecture halls where I was in the previous hour, we don't see you in the next hour, but vice versa, I tend to go there where you were, so that from that we can see these asymmetric associations. And those we have, I mean, they are incorporated in HMSC in a way that you can just bring the species occurrences in the previous time point or abundances through this X data. And then you have this issue that you typically have a lot of species, and then you have a lot of species by species parameters to estimate, and that's why then in practice you have to use some of these dimension reduction tricks. And let me illustrate this a bit. That there is this 2017 paper where we looked at this. I mean, others have been looking at the same kind of things before, but this is the first time that we were looking at that, where we are estimating these. This is what I showed already, that we try to estimate these asymmetric association matrices, and and we do it in this paper with 4 different models. Model 1, we assume that there are no interspecific interactions, that we only model within species density dependence. Model 2, full interactions. Let's just try to estimate all of these elements of this with 100 species of this 100 times 100 matrix. We just try to estimate 10,000 numbers. We see that in that case we do very well with explanatory power because we can explain everything in the data. We have like more parameters than data maybe. But then in the predictive power, that model is very bad. And then we have this sparse interactions model. I mean, these results were generated, I think, with the MATLAB version of HMSC that we were developing at that point. But now you would do it by this sparse interactions model by putting those species abundances in the previous time step into X data, and then using X select to do this variable selection among them. To say that you expect that only a small number of them are non-zero, to find those species pairs that really interact. And then we have this model 4, which is these community level drivers that assumes that there are some linear combinations of the species abundances that do matter. For example, the sum of the praise would be a kind of a conceptual example. So this you can now implement in HMSC using this reduced rank regression by putting those covariates into this XRRR. So we have not, there is not like an HMSC time series model, but you can utilize HMSC to do these models. And then there are some developments with Jenny and Gleb, where we, in a sense, kind of compare. Where we look at, I mean, what is one issue with this way of implementing the time series models is that we allow in HMSC like some residual in the response. We don't think that okay, we have observed species completely and all of this. But then when we use the species abundances as predictor for the previous time step, we don't account for kind of the uncertainty there. So you could think that, oh, it's much more natural to think about the true abundance as kind of some kind of a latent, unobserved variable that then matters, and then we have observations on that. So then this approach that Jenny and Leif are thinking about the counts or compares this approach to that, and does it do something else? You compare also maximum likelihood to Bayesian and basically you are kind of asking that is this weak and dirty approximation, you know, which kind of exists in HMC, does it give you the same results as if you do this kind of a more beautiful latent underlying true process approach, and when does it give different answers? And because you know that more beautiful approach is more tedious than to fit and to define, so it has not been implemented into HMSC. There is a separate implementation of that to kind of a simpler case studies where you don't have all the other random effects, anti-phylogenies, anti-traits, and all of this other stuff that you need to care about in HMSC.
Sorry, if I understood correctly, this is you can define them when you run the model, but does it also produce the species association matrix that would be asymmetric?
Yeah, these models that I talk about, it gives you that, and I think here we see an illustration of I don't think this matrix. Yeah, this matrix is not symmetric. This matrix that you see there, quite small, is the estimated species-to-species association matrix from these real data that were used here, which is not symmetric. It's estimated from the time series data. Okay, any other questions? If not, then let's talk about these R package features of HMSC, and Jari will tell about them. Okay. Joo. And so while Jari is setting this up, we need to leave this room at 2, because then there is something else happening here. So then let's go to the breakout rooms and maybe we squeeze one of them all together and continue there.
Right. There's something wrong here, but I don't know what.
Kokeillaan se avaamaan tuon folderin, niin näkyykö se siellä?
Folderin on lateessa, suostuu avaamaan sitä.
Eikä se näy täällä.
Niin jos on siellä, joo.
Missä meillä on?
Tuossa on USB Drive D.
Joo.
Okei. All right. Okay, it's here. So now something technical again, but not technical in Gleb sense. We have no equations here, but still about techniques, and not so much about the things of the future, but things that you can do with HMCS now and how we are going to develop it. So we are having this package in GitHub, that address. If you want to see what's happening, go there. You have something to tell us, go there. There are issues, you can report things, you can make your wishes and so on, and we try to just answer to you, communicate with you, and we are often friendly. It's not guaranteed, never, but we do our best. And also, this package has no compiled code. There's no C code or anything like that. So that means that if you can install the CRAN package, you can also properly install directly from here the working version, development version, and that may solve some of your problems. Of course, it can always happen that development version is not stable because we develop it. So we try to keep it working anyway, but there always can be surprises, so it's of course safer to use the released version. But anyway, you can try it. So now, just for this course, we had 8 days ago new release of this package that has some new features. And now I'm going to explain some of these things and some that's going to happen after that. So main thing is that we sometimes have problems with so-called bad updaters. You run some analysis, say 3 months, and then it is trashed, just with cryptic error message. Now we try to recover from those. What about that? Then we have now an option or possibility to add more samples to your models by adding new chains. So if you think that you need larger sample, you can just repeat your analysis and add chains to your old models. Then, as you know, the prediction and this compute predict values can be, cross-validation can be extremely slow. And now we have more accuracy parallelization for that, which can help if you have CPUs or cores to spare for this analysis. And then we have improved support for spatial models defined as distance matrices instead of spatial coordinates. That can solve things like, for instance, how to measure distance along rivers. And there are many more news, and if you want to see what are the latest news in your version, just issue rcommand news package HMSCS. It will give you the news file. Or go to this GitHub page and see the news there. And of course, I know that always in courses like this, we find new bugs. And this means that after this course, we're going to have pretty soon a new release. Okay, now first about these errors. There are three kinds of errors. There are evil errors, good errors, and nasty errors. Evil errors is the worst one we can have. That means that the software runs, it gives a result, but the results are wrong. But there's no way to see that they are wrong. Nothing warns you about that. And that, of course, is something that we try to avoid. We always test our code and compare to other things, try to verify the code. Of course, these hairy models, like these models are extremely difficult to verify. It's difficult to say what is the correct result actually. It's always a random process. Anything small changes, and everything changes in random process. It's a random chain. Step one changes, and all is changed. But anyway, we do that. Then we have good errors. That are errors that you should be happy about. For instance, when we tell you, that means that we catch the error and warn you. So you should be happy and grateful to us. If you get an error message that, say, for instance, that names of rows of trait matrix should match column names of Y data, be grateful. If you don't catch that error, you will later get errors like trying to use zero-length data, mismatch of dimensions in some calculation, and that's completely incomprehensible. Now, these are good errors, and usually we try to make them early into analysis, so that you don't have to run weeks to get the error, but you can get it in some seconds. And then you can fix your analysis. But then we have these nasty errors. These are the errors that we don't handle ourselves, but they come from the abuses of the R. And they often are very difficult to understand. You don't know why they are there. And if we find these, we try to change them to good errors, so we detect the danger and warn you before you go to a weeks-long analysis, months of runs. And many of these are now caught in this latest version of R. If you go to GitHub issues, you see that many people have had this kind of thing. We have that in the run iteration 30,516. The run is stopped. No, all right, this is one of these examples of these nasty errors. How many of you understands what it says here? And why? You have nothing like IV. What is Joel? What does it mean that leading minor of order 3 is not positive definite? So this is the typical error that I got from some updaters. We know that this shouldn't happen. Mathematically, this shouldn't happen. All things that we have there are positive definite. Of course, there can be errors that we're making code, but anyway. But we are dealing with numbers here. Some of these numbers can be very small, very too similar to each other, differently scaled, and then you get this error. Often it happens in corner cases, like plenty of missing cases, missing values, and then your matrix gets somehow unbalanced. So what we now do, and this typically just comes from these updaters. For every iteration, if the chain, you update all your parameters. Like we see here, we have sometimes 16 updaters here, at least, that are usually run in one iteration cycle. And these are not deterministic. They don't happen at once, they don't happen always, they can happen sometimes, and they can happen after long runs. So how we deal with this now is that we try to catch these errors, and what we do then is that we don't update that parameter, but we keep it all value and then hope that the next step, next iteration, the updating will again succeed. What is recovery? It's here. All right. And if you got this kind of cases, you get a message that you have failed updaters in certain chains. It tells you soon after your run that these some of the chains has failures of updaters and which updaters you had these problems in. And if you do not have many failures, you can safely use the chain. If you have too many, you can't use. What is too many? I don't know. But it's pretty, I would say that you are pretty safe if you have less failures than is your thin. Then you can anyway assume that at least once during this iteration cycle, this parameter was updated. It may be that if you are saying 1% of failures, it could be something that you can tolerate. But if you have plenty of these failure messages, which also are permanently saved with your result object, and always print when you look at the object, then what you can do, that you may do, is that you remove that failed chain and use the chains that were successful. And the way, for instance, to remove the second failed chain is to give its value null. So that command here, model post list number 2 equals null, is made to null, removes that chain. And if you have very many failures, then you may consider or reconsider your model. It may be too complicated, too difficult, too overdefined, and you get problems because your chains, they drift in strange territories where nobody should try to go. So nobody should go. And just on this Sunday, we found one of this model, what's just fungal model that of today, that gave this error always. And we found out that if you disable one updater, gamma eta, then this model will run. And now Gleb changed the code so that the GitHub master so that nowadays this gamma eta force is the default in sample MC command. That's a pity because usually this gamma eta improves results in all terms: larger effective size, sample size, these reduction factors closer to 1, better predictive ability, and so on. But it seems that perhaps if you have very many missing values, it can also give you a problem. The funny thing here is also that the problem doesn't come from gamma eta. That runs usually. But next updater, beta lambda.
Yeah, just to make the point that when you say that this updater improves the results, like you explained, it improves the mixing.
Mixing, yes.
But if you can get your model mixed without that, then the results are the same.
Yes,
the
yes.
estimates are still exactly the same.
Yeah, you only need longer time for that.
Yeah.
All right. So there may be errors, and we are happy to get error reports. Go to GitHub, go to issues, tell them that you have a problem. And it's always useful if the error, if your reports are useful for us. So we should know where the error happens. And one trick here is to use traceback after error. That gives you a long list of commands that leads to the failure. It's a pity that this doesn't work for parallel models, because these chains that disappear in parallel processes, you only get the start of parallel command. So in that case, if possible, rerun your code with non-parallel, that means in parallel 1 chain, and try to get the error. And also use setseed, try to find a sequence that fails soon. Because if we can repeat the error, replicate the error, we can fix it. I hope so. And there are chances to fix it because we know what to fix. Otherwise, it's just like a blind watchmaker, doing something with your code and hoping that it helps. But if we know where the failure is, we can try to solve the problem. All right, now you already saw that you may have to remove some of your chains. happily, you can now also add chains to your models. It's very simple short command called C, combine. The standard R command that combines different data structures. And this combines these sample MCMC models so that it adds chains from models together. For that, the models themselves should be similarly defined, also for thin, sample size, transient, things like that, but of course for all parameters. We do some checking of this similarity. But we won't stop you. We give you 6 foot, we give you enough rope to hang yourself, and then a bit more. So you can do whatever you want, but anyway, you were warned if you try to do something that we think is stupid. And one thing that's very important that we also actually check is random seed. Do not repeat your analysis from the same random seed, because that doesn't give you any new observations. It just duplicates the old models.
But it gives you very, very good film.
It gives, yes, always duplicating data or multiplicating data always helps in goodness of fit or anything like that, but it's not right. All right, then the slow thing here in...
Hey, Jari, sorry to stop you, but I see that we will be kicked out in 3 minutes.
Yeah.
And you still have a couple of slides, and I think it's very nice to go through this not in a hurry. So why don't we now move to the breakout?
All right, let's do so.
And then we continue there.
Yes. Okei, mistä mä saan ton pois ton tikun? Tuosta jostain. Eject.
So those of you in the Zoom, we will come back in 5-10 minutes after we have changed the room here.
Okei, taitaa olla safe. This should be moved somewhere from here. Okay, do you see it from Zoom? All right. We'll get this moved. All right. So, as you know or have seen, this cross-validation is very slow. Where is my mouse? The cross-validation can be very slow, and the problem here is that the HMSC is not very sensitive to sample size, number of rows. And flip side is that even if you only take half or 4/5 of your data, it doesn't run much slower, much faster. So it takes almost n-fold times to run prediction than run your original model, because you always have to predict the whole model again. I go closer here so they hear me here. And we can have parallel running here. And this basic function, compute predict values, the old function, it could run for each fold, it chains in parallel. But all chains all folds were run serially after each other. Now what we do actually here in this new function that's still experiment, that is p-compute parallel compute, is that we can run n chains times n folds in parallel. Of course, if you already used all your cores, CPUs, for parallel chains, then you have nothing to spare here. But if you have cores in reserve, you can run all of them in parallel. And the trick actually is that what we do here, if you want to hear that, is that actually what we do is that we rerun all these sample MCMC models with one chain. That each of these can be run in parallel process, and then we use C function to combine this back to what we had originally. So if you have change to share, then you can use this. And one smaller thing is we don't use pre-scheduling here now. Usually in R, when you are running parallel processing, you decide first which process to go to which core. And all, if you have, say, run 4 chains simultaneously in parallel, it waits that all of these chains are stopped, and then it starts new batch of 4. And if you, and 5 comes, after 1 comes 5, after 5 comes 9, and so on. It's always determined section here. But now we don't have this pre-scheduling, which means that as soon as one of these chains is finished, a new chain is started there. Meaning that if these chains, like they often do, run very different times, you can also run a little bit faster with this system here. Usually you want to have pre-scheduling because that's faster, you don't need to communicate. That's only faster if you run for some seconds. But now we're talking about minutes or hours. So this can help here. And the plan is to replace the old function with this new one. But now, because this is a new one, I want to keep them both there so that you can compare the results. The results are not exactly similar because we are doing things a little bit different order. So change. Perhaps only the first chain or first fold can be identical with the old model. But then this sequence is unpredictable. But anyway, what I've checked, the results are similar, give similar kind of results close enough to each other. And also when I go inside there and change the random seed to internal one we used earlier, first part of the analysis can be similar, and the expected values can be quite similar. But these observed values, the predict values, for scalar observation, they can change. Another thing is that we also have parallel processing in predict function. You usually don't need it there. It's pretty fast anyway. But if you are doing species cross-validation, that Otso didn't mention at all in his lectures now.
Conditional.
Yes. Then this can be much slower than all other complete values function. But here you can have as many cores as you have, because we are doing this parallel processing over posterior predictions. So if you have a posterior sample of 1,000, you can divide this for 8 cores to pieces of 125 chunks, and these are run each in parallel, and the results are combined. So this can speed up results, but of course you need cores, you need CPUs for this. Then some words about speed in general. There are some things that you can do already now. Let me doing really fast, really advanced code, but you must wait for that still for a while. But what you can do now is you can try to improve your computing platform. And some of this can be easily done if you haven't done it yet. Point is that most of time in HMSCS, we are spending time somewhere else in our own code. We are spending it in matrix algebra. And matrix algebra is done by external library called BLAS, or Basic Linear Algebra subprograms. And R comes with so-called reference BLAS, which is just the plain code like it's done, but it's not optimized. You can optimize BLAS to run in your software, in your hardware, and in your operating system. And this can give you some 10, 20 times speed up compared to reference BLAS. There are many things that this reference BLAS, what this optimization do. So they can use parallel process of some matrix algebra, because several problems can be solved so that you solve matrix by slices. And the slices can be handled simultaneously in parallel. That will give speed up. Also, they can be vectorized, because in matrix algebra, you typically use same instruction, same command for multiple elements of matrix. And you can process many elements in one clock cycle, meaning again speed up. If you just change your BLAS from reference BLAS to something that's optimized for your computer or for a computer system, you can run faster. There are many alternatives for different platforms. In Linux, they usually use OpenBLAS, which is open software and pretty good. Then in Intel systems, the fastest may be Intel math kernel library. At least so they say in CSC, Central Scientific Computing in Helsinki, in their tests. But difference to OpenBLAS can be rather small. And in Macintosh, Apple, you can use Accelerate framework that's optimized for processors. And if you happen to have M1 or M2 ARM architecture, that happens to have a 16-core matrix algebra component unit, hardware unit. And that can give some 20 times speed up compared to not using that one. And 20 times, that means that instead of 3 weeks, you get the results in 1 day. And that's a big speed up. And how they take this into use, that differs with your system. It's easy, and you find these instructions in CRAN manuals. There are these FAQ files for different operating systems, architectures that tell you how to do that. And then there's this R installation administration manual that tells about these things. So it's very easy in Linux and OpenBLAS. It's very easy in Apple. It's more difficult in Windows. And if you want to use MKL, that's Intel MKL, then you need to compile your R as well with Intel compilers, ICC compiler. Anyway, for instance, now one consequence of using OpenBLAS or BLAS may be that it doesn't speed up your analysis to use several chains. For instance, when I run this test in Otso's 40-core Intel computer, and I happened to be the only user of that computer at that time, I saw CPU uses of 4,000% for my process, meaning that all 40 units, 40 CPUs were used by my R code, and not in chains, but in BLAS. So if you run then 2 chains, each of these chains can use 20 cores in BLAS. If you use 4 chains, they can use only 10 cores in BLAS. So the time can be about the same, because the BLAS is doing the optimization, not R level. But usually you get huge speed up. Then some more special things that may not be so widely used anyway. But anyway, we can usually define spatial models by getting spatial coordinates, and then we calculate distances from these coordinates within R, within HMSCS. And these distances are actually used. And now you can also supply your own distances, distance matrices, which you usually do in case if you are not satisfied or don't want to use, say, Euclidean distances like or geodesic distances of longitudinal data. Like, for instance, want to have distance along rivers and not across land. And in that case, you can supply your distance matrix. And although we usually have this, or we internally use these distance matrices, the support for them has been a bit uneven. In some cases, they fail. I've tried to improve these cases so that in most cases, you get similar results if you supply coordinates or Euclidean distances. But there may be some cases, or sure, there are some cases that I haven't tested. And it's your task to find those cases and report them to me, and I can try to fix them. But that anyway is the goal. There are some exceptions here. GPP models, spatial models, they need coordinates because we need coordinate points grid for those models, and there's no obvious way of providing grid for distance matrices, especially when these are not Euclidean. Now, anyway, one thing that you can also, that we also do accept infinite distances. Infinite distance means that ignore, for this case, spatial dependence. It's so far away, these points are so far away from each other that they have no spatial dependence. So that's again something, for instance, that you have river distances, you have several rivers. And these river systems are from infinite distance from each other. So you can impose it here. You only have distances within one river system, but not between river distances. You can also, at least almost, have infinite coordinates. Actually, I'm not sure if it exactly works, because it seems that if you are infinite coordinate for one point, that will have infinite distance to all other points. But what is the distance between two sets of infinite coordinates? It seems to be not a number. So this could be perhaps something that we must have a look at. Okay, then finally, one thing that, because I started to use R in 1990 something. It was before tidyverse. So I had a little bit different tradition of doing things. And one thing that I think that every R object should have is a call component, and ability to update your results automatically. It doesn't go to Otso's toolset or just script set, but it's very handy anyway. And since I came to R, first grand release we have had this call component, but nobody seems to use it. So now I saw how to use it. First, this is the example data from the package. And I set it as model M here. Just say get call M, and you see how this function was called. And that may be more informative for you than just the brief output we had there. I think actually we could add this print output also, this call interface. And one funny thing here is that when you also have this call component for random levels. So you can check easily how did you define your random level earlier. And one thing here is also that when you have a call component, you can update your model. So if you want to keep most features of your model, but change something a bit, just say update and the things that you want to change. So for instance, if you want to change the X formula and distribution here, we just give the old model update M, that model here, use this formula and this distribution. And you get new model. Yeah.
I have a question about this update example. Let's assume that I have fitted the model already.
Yeah.
I have a posterior sample, and then I run this update formula that you show here. Does it then keep kind of the old?
No, it removes posterior.
Okay.
It removes posterior.
As it should.
Yeah, it should, yes. And also, for instance, in lots of scripts, you don't have formulas like this, but you have a variable called X formula. But now, if you change that variable X formula some way and just say update N, it will use the Nuix formula. Because it will read again all these. Actually, what it does here, it is rerun this HMSC with this command and use all that you have here, like default or extract data. If you change that data, it will update you as well, even if you don't give it expressly here. So this is one thing that comes very handy when you want to explore variants of your model and keep the old model otherwise untouched. So this is what we used to do in old times before tidyverse. All right, I think that's the most things that we have now. I have now about this development. Like I promised anyway, new version is coming in autumn anyway, because you found again errors or problems with code. Okay, thank you. So anything to ask about this development process or some things that you wish to have in say user interface or kind of other features here? No, okay. Upstairs. No, thoughts.
Well, I have a question, but not so much into the river example, the river situation that you were playing, just making me think that maybe it's more related to the fantasy or anything that you were saying before. How can be included the fact that it's a river, that the direction is downstream?
No, we don't have anyway. Our distance must be anyway now symmetric.
This is okay.
Yeah, we can't handle down river and up river. But this currently would require much changes in code.
Except that when you have this time series data, you can account for that by yourself by putting into X data as predictors that you know which species were present upstream before this time step when you are looking some other species downstream. So in that way you can generate those asymmetric matrices yourself, but then the distance is symmetric, as Jari said, and now this feature is just that whether we calculate the Euclidean distance or whether we calculate the distance along the water.
Yeah. Anyway, I think the same features have now with using time as a spatial coordinate, because that's also symmetric. You can go back in time quite easily in R. Unless you do like Otto said, but anyway, the distance model will be symmetric in time as well. So future influences what we have now. Yeah.
Okay, looks like there are not more immediate questions to Jari. And now basically we have still 1.5 hours remaining and we have no planned program. So now this is the time for discussion about anything that you would like to discuss about, or still go into some small groups that, hey, could we look at this data set together and get some advice for that? That's now the time for this, or then it's the time to, you know, just relax and have a break, whatever you would like to do. But I saw that Carlos has some question that you would like to make.